All right. Okay. So Dmitry Kubrak is talking about cohomology of classifying cycles.
Yes. Thank you for the opportunity to speak and introduce myself as well as some part of what I have been thinking about lately. And yeah, so it was actually a great luck that some of the main players that I'm going to talk about were already introduced by other speakers. So I hope this helps, but let's see. Anyhow, for now, let X be an algebraic variety over complex numbers. And if you are not really doing algebraic geometry, the example to keep in mind is probably just the set of solutions of some polynomial equations inside the n-dimensional complex space. And having such an algebraic variety, we can consider the topological space of its C points. So in this above example, I would just consider the set of solutions with the topology induced by the, say, Hermitian metric on C to the power n. And yeah, after considering this topological space, we can associate to it quite natural linearly algebraic variant, namely as a graded ring of singular cohomology with complex coefficients. And as, for example, Sasha Petrov discussed in his talk, if X is smooth, so smoothness is some regularity condition. If you were looking at the system of equations, it's some Jacobian criterion which defines smoothness. So yeah, if X is assumed to be smooth, then as was shown by Grothendieck, this singular cohomology actually has a purely algebraic description, namely it can be identified with the algebraic de Rham cohomology, which in turn is defined as cohomology of X in coefficients with certain complex, which is called the algebraic de Rham. And also, if we further assume that X is proper, which on the level of the C points essentially means that the space is compact, this de Rham cohomology can be further decomposed as sum of what is called Hodge cohomologies. So these are double graded groups, and ith jth graded component is given by jth cohomology of X with coefficients in I forms. Okay, and so Sasha in his talk was studying what happens with this sort of Hodge decomposition property when we consider varieties over finite fields. But I will be considering different problems, so different sort of problem, namely what will happen if we try to describe singular cohomology of X of C, but not with C coefficients, but FP coefficients. And here for a moment, let's suppose that X was actually defined over integers. So yeah, let me not define precisely what this means, but in this example where we were considering a system of solutions of some polynomial equations, I would want these polynomials to be defined over integers, so that this means that their coefficients are integers. And yeah, so if X is defined over integers, we can define this reduction modulo P. So in the above case, we will just reduce this polynomials modulo P and consider the sort of algebraic variety of solutions. Okay, and returning back, this definition of algebraic de Rham complex actually makes a perfect sense in this setting of varieties over finite fields. And so we could consider the de Rham cohomology of the reduction given this, and maybe a naive or even crazy guess would be maybe the singular cohomology I actually computed by the de Rham cohomology of the reduction. And the answer is that not really, or actually in most of the examples, the answer is really not. As I want to illustrate in this example. So yeah, let's consider just the affine line, and then the topological space of C points is given by complex plane, in this case, which is contractible. And this means that the singular cohomology, even with FP coefficients, are just computed by FP in a single degree 0. But if you compute the de Rham cohomology, in this case, then what you get is the following complex. So you have a polynomial ring over Fp mapping to a free module over it spanned by dx via the usual de Rham differential. But now specifics of characteristic P is that if you plug in inside the differential a monomial whose power is divisible by P, then the result will be divisible by P itself. And since we work with modulo P, it becomes 0. So it means that 0 is the rank cohomology of A1, which is exactly the kernel of this map, is in fact isomorphic to polynomial ring in x to the power P itself. And yeah, so the first thing you should notice here is that this space is actually infinite dimensional. And so, well, there's no way it resembles the singular cohomology in this case, even by rough size. But actually, if you assume that X is proper, oh yeah, and here I also assume that X is smooth, at least it's true that the rank cohomology of the reduction will be finite dimensional. And in fact, in many concrete examples, you can non-canonically identify the singular cohomology of FP singular cohomology with the rank cohomology of the reduction. Examples being like projective space or Grassmannians or abelian varieties or K3 surfaces and many other examples. And in fact, a recent work of Batmore Schulze, where they developed a inf cohomology and the further development introducing the prismatic cohomology, shows that this idea is not that crazy, and the difference between two things is controlled by something relatively explicit and can be described by an integral Peyde-Hodge theory. And yeah, I hope to return to explicit thing which controls it. But okay, so this was an introduction of what is classically known for in this world of schemes and algebraic geometry. But yeah, I promise that there will be some classifying stacks in what I was going to talk about. And yeah, so now let's pass to that. And here, yeah, so main person who initiated research maybe here is Bert Totaro, who is actually here and will be here for the special year in Peyde geometry. Yeah, so let's consider the following. So let G be a split reductive group over Z. I won't try to define what this means, but rather just tell you what are the examples, some particular examples, like you can consider a multiplicative group or the group of invertible n by n matrices, or orthogonal group, or its double sheet cover given by spinor group, or projective linear group. So all these groups, they have algebraic geometric models which could be defined over integers. And given such a group, we can consider its C points, and this would give a topological space, but also it will have a group structure. In fact, it's a V group, but in particular a topological group, and to any such topological group, we can associate its classifying space. So the natural object to consider, yeah, now we can consider its singular cohomology with FP coefficients. And this ring is classically known as a ring of characteristic classes, G of C. And we can ask a similar question as before. So alternatively, we can take the reduction of G modulo P, and in algebraic geometry, there is an analog of classifying space construction, which is given by taking classifying step. And yeah, one can also extend the rank cohomology to the stack setting. And yeah, so question which Bert asked was under which assumptions or whether these two things agree. Is there a natural isomorphism between the rank and singular cohomorphism? And in fact, it turns out that answer is almost yes. And let me give the only definition in my presentation here. So it's certain condition on a prime relative to the choice of this reductive group. And yeah, so a prime G is called torsion over G if when I consider the singular cohomology of C points of G with integral coefficient, this abelian group has non-trivial P torsion. Here I just want to emphasize that this singular cohomology is just some finitely generated abelian group. And this means that the set of torsion primes for a fixed group G is just some finite set of primes, some singular primes. And yeah, also let me just mention that Borel showed that this condition on the cohomology of G is actually equivalent to the same condition for the classifying space. Then the theorem which Totaro proved is that if P is non-torsion, so P lies outside of this finite set of primes, then in fact this singular cohomology ring is isomorphic to the de Rham cohomology ring. However, this isomorphism is not canonical. And in fact, there is no natural map in general in either of the directions. Okay, and yeah, so just to give you an idea how this torsion prime looks compared in different situations. So I'm not sure when exactly I started.
It's 225 on this.
25?
225 on this.
Okay, okay, good. Then I can probably say a couple of words. So in the case of GLN, the general linear group, if I consider the C points, this actually is this group is homotopy equivalent to the unitary group of size n. And yeah, so this group, for example, appeared in the talk by Arpon, and maybe in the talk of Allen as well. And yeah, so if you consider its classifying space, then it's a classical computation in topology that the integral cohomology ring of this classifying space is given by polynomial ring in Chern classes. So these are certain elements of Ci, and degree of each Ci is 2i. And yeah, in particular, we see that this is a torsion-free abelian group, namely just all monomials and Ci's give the basis of it. And there are no torsion primes in this case. However, any prime is a torsion prime for some discrete reductive group. Namely, if we consider G given by projective linear group of size n, then it's not hard to compute that a second singular cohomology of its C points, in fact, is given by Z mod n. So in particular, every prime which divides n gives you a torsion prime. And you can show that this is the set. So the set of primes dividing n is the set of torsion primes in this case. And let me just mention that in the case of orthogonal group or its double cover given by spinor group, the only torsion prime is 2. Okay, and so yeah, let me just show you again the theorem Totaro, which was describing the relation between the Raman singular cohomology for non-torsion primes, and Snatchell talks what happens for torsion primes, whether this theorem extends there. But example also computed by Totaro shows that no. Particularly, he was able to compute that if you consider 32nd the Ram cohomology of B spin 11, then this is strictly bigger than the dimension of corresponding singular cohomology. And this, I think, really stays the minimal example in this reductive group framework for when the inequality breaks. Equality breaks, becomes strict inequality. But in a way, you can fill the gap, and this is given by my joint work with Artem Prihodko. And so one of the results we show is that it's always true that the dimension of the Ram cohomology of the reduction, the classifying stack, is greatly equal than the dimension of the singular cohomology. And moreover, you can fairly explicitly describe the difference, namely it's controlled by a certain other cohomology theory, namely mod P prismatic cohomology of the classifying stack BG. And this prismatic cohomology, it's naturally a model over power series ring over FP. And more precisely, the difference is controlled by the U torsion in this model. And let me just mention that actually our theorem works slightly more generally for quotient stacks, where you consider quotients of smooth proper schemes by reductive groups. The result is interesting, or like just the question of comparing this Raman singular cohomology. So yeah, I forgot to mention that actually for some particular examples of G, this computation of this cohomology ring of singular cohomology of BG of C is a very hard problem. And for some groups, it's not known still. Yeah, on the other hand, on the Ram side, you can show that in this case of classifying stack of reductive groups, so Sasha in his talk was saying that you don't always have Hodge decomposition in characteristic P, But for reductive groups, for classifying stacks of reductive groups, it does hold. And this gives a splitting of this de Rham cohomology as a direct sum of bigraded pieces. And each of these bigraded pieces can further be interpreted in terms of representation theory of the corresponding reduction of G. And it's given explicitly as cohomology of G with coefficients in some symmetric powers of coadjoint representation. And yeah, so even though G is a reductive group, in characteristic P, it's no longer linearly reductive, and these cohomology groups can very easily be non-zero. And again, it's actually a very hard problem to compute them for small primes. And yeah, so this theorem, or even the earlier result of Bert, I mean, it gives an interesting relation between representation theory of G in characteristic P and some topology, classical computational topological problems. And you could use methods on both sides to get some new information on the other. And yeah, let me just finish with what things I would like to think about in IIS during this year related to what I just told you. So one very interesting example of this potential comparison is when G is equal to the projective linear group. So for torsion primes, in fact, the answer for the singular cohomology of BG is not known unless P is not equal to M. And so based on some computations, or yeah, I have been thinking about this for quite a long time, I actually suspect that it might be true that this singular cohomology ring is just isomorphic to the de Rham cohomology ring, even though both things are hard to compute. And in fact, the de Rham cohomology ring is more computable. I can't really give a formula for any precise like cohomological degree of the dimension, but at least there is a very natural complex which computes the cohomology. And so if one wanted to compute it, they would be able to. And another more theoretical question is so whether this theorem, so I said it works for quotients of smooth proper schemes by reductive groups, whether it can be extended to more general class of stacks. And me and my co-author, we have a candidate for what this class of stacks is, but not really have a proof for why it would work. Yes. So I would like to find the proof. Okay. That's it. Thank you.
Question.
When you say that you have put the composition for the Rham
Yes.
do you mean the spectral sequence that generate, or do you mean you have not heard the composition?
Actually, I think in this case, I mean, it's not written down anywhere, but I think there is a more accurate statement. Yes. So the Hodge cohomology is isomorphic to the Rham, even as some higher object, first of all, and it's even functorial in a way. I think it should be isomorphic as the infinity algebra. Sorry.
So does this more general class of stacks you alluded to at the end include things like A1 mod GM?
Right, exactly. So yeah, it should be. So there is a notion of formally proper stack by Daniel Halpern-Leisner, which is essentially saying that you should have Gaga theorem, which you usually expect for smooth, just proper things. And I expect that this should be the key condition for having this sort of comparisons. And it does hold for X mod G, where X is smooth and proper and G reductive. Yes.
I got this, what you said was a sort of essentially minimally counterexample involving spin 11.
Yes.
Can you say something about the 11? Does it have to do with the 11, you know, the
Yeah.
11, like M111 is the first time?
So actually, yes, it's, I can tell about this. So actually you can compute cohomology rings, de Rham cohomology rings for all p-spin M's over F2. And so key condition when the Rham cohomology differs from singular is that N should be compared with, should be 3, 4, or 5 modulo 8. And this is related to some combinatorics of Clifford algebras. But then like if you take 3, 4, and 5, in this case, SO N is too simple. Like there are some exotic isomorphisms with other reductive groups, and yeah, you don't get this torsion there. And then the first one, which is 3, is 11. 3 modulo 8 is 11. Yes.
You said that it's difficult to compute in some cases with cohomology ring, what is the input to the computational problem exactly? What do you know and what do you?
You mean what is known about this?
No, what is the input to this computer? What are you given?
A reductive, sorry, you are given, yes,
N,
yes, you are given a reductive group, so it's some combinatorial data, maybe like root.
So with a fixed n.
With a, yeah, so for example, here you could take PGLN with a fixed n, and then you also can vary p. And then if p is outside of n, then it's covered, for example, by Bird's theorem. But if p divides n, it's actually quite complicated. Oh, and I forgot to say that actually these two things are identified in one series of example by, it's due to TODA, some classical topological computation. And this gives me hope that also that this could be true.
Or question?
When you
Yes.
speak of cohomology of bit v, can I think bit v as being a simplicial space? Or definition?
Yes, yes, essentially. Or you can write can extend from smooth schemes as an object on an infinity category of complexes. But then you can show that it's actually computed by any simplicial. But this, so problem is that this simplicial sort of presentation is not really helpful here because the rank cohomology of affine pieces is very huge. And then, so we need some global arguments rather than.
Okay, thanks.